Okay, so now we're going to look at the top-down approach to solving this particular knapsack problem. So let's think about the items we had. So we had items A, B, C, D, and these are the weights of the items. And then we also had these as the profits, and the maximum weight, I'm going to use an arbitrary number here, that's why I'm just using C there. So let's ask ourselves how we can solve this. So we are starting like that. We know the maximum weight my knapsack can take is C, and I have 4 items. In the top-down dynamic programming approach, I'll be asking myself, starting with the last item in my list, should I include that item in the knapsack or should I not include that item? And with this top-down approach, I'm going to be reducing the number of items available to me. So I start with 4 items. I ask myself whether I'm including D or not. And then in the next sub-problem, I'll only have items A, B, C. So I'll also be asking myself, am I including the last item C or not? And then I'll only be left with A, B, and I'm going to do that up until I have no items to choose from there. So in a top-down approach, I start with the last item, and I only have one decision to make. It's a 0-1 knapsack. So it means, is the item in the knapsack, so that's a 1, or is it not in the knapsack, so that's a 0 there. Which means my problem is going to have 2 sub-problems. The first one is, if I include D here, which means that if I include D, the profit I'm going to make is going to be the maximum of this recursive function that I'm going to explain, plus the profit I get from the last item D there. So this would be 10 as my profit, plus the profit I get from this sort of recursive function here. So that's the first option. Or the second option is I don't include D. So it means like my items reduce, so I'm not going to include D in the next sub-problem there, but the sort of weight does not change. So let me just get to the previous one. If I decide to include item D in my knapsack, it means now when I'm left with only 3 items, the weight available for me has reduced. So the weight available for me in this particular instance is not C anymore. It's C minus the weight of D that I was able to clear out over there. So keep in mind the maximum weight reduces after including D in the knapsack, and also the number of items I'm working with I'll only be left with ABC. So I'm going to be recalling this function to maximize what is the maximum profit I can get from this 0-1 knapsack when I only have ABC as my item and the maximum weight is C minus the weight of D. So that's the first layer. That's if I include D. The second layer is, what if I don't include D? It means that the profit is not included of D, but the maximum weight also does not change, but what I'm reducing now are the items. So if I decide to ignore D in my final knapsack, it means I'll just be trying to find what is the maximum profit I can get from items A, B, C, if like the maximum weight my knapsack can take is C, because D does not influence the weight at all. So these are going to be the two problems here. And to get the maximum I get here, it's going to be the maximum of this branch versus the maximum of this branch. So the maximum profit where I include D versus the maximum profit where I ignore D there. And this sub-problem continues. What if we are now at this sub-branch here? So when you're at that particular sub-branch or that branch there or that leaf, I'm losing it, we can either include C, which is now my new last item, and if we include C, the profit I'm going to make is going to be the profit I get from C, right? Plus the profit of this particular knapsack. But in my knapsack, after including C, I only have 2 items available at my disposal. So A and B will be the items that I'm putting in my knapsack. And the weight I'm going to have is going to be the weight that I got from the previous function, which was C minus weight of D, but I also have to subtract the weight of C. So the same way in this first instance, I had to subtract the weight of D. Here also, if I include C, I have to subtract the weight of C, and I remain with 2 items. So I'm always removing the last item available, and the weight reduces based on whether I include it or not. Also, the profit increases if I include that item or not. And the second branch there as well is what if what if I ignore C? So the maximum weight remains the same. So it's still going to be C minus the weight of D, what we computed from the previous function, but the items remain 2. So I've decided to ignore C. I'm not going to include it. So it means I'm only going to make my optimal choice from A and B. So each and every single time, this will tend to be the optimal sort of solution you're making. And even the second branch here where we ignored D, we'll still make the same one. So it's either we include C, so it means like we reduce the weight of C there, and we're only left with items A, B, or we decide to ignore C, which means the weight remains the same, and now I'm left with only items A, B as well. So just my apologies for that. Even on this, we are reducing the item. So if we decide to ignore C, it's not supposed to be part of my end knapsack. So my recursive function is not supposed to be there as well. So I'm left with AB. And this is going to continue up until we have no items in the knapsack. But now there's a caveat here we need to be aware of. So what's the first caveat? This only works if the weight of the item we are looking at a particular instance is less than the space available in the knapsack. So at any given front, we're asking ourselves whether if this item B has less weight than or is equal to what's available in the knapsack, then I can include it. If it has a higher weight than what's in the knapsack, then it does not make sense to include it. So this two-branch sort of tree that I've created here only works if the weight of the item is less or equal to the space available in the knapsack. The second question we're going to ask ourselves is, what are the base cases? And that's what I'm going to answer in the next sort of section here. So let's ask ourselves, what if the item weighs more than the available weight? So this is the two-branch problem. This is the recursive problem. So we're trying to maximize what we get from these two branches. And the first branch, I include D. The second branch, I don't include D at all. So, but here we know if D has higher weight, so this is what you're asking, if D has higher weight than C, then it means we cannot include this particular sub-branch. So we cannot include D so it means this sub-branch is irrelevant if the weight of the last item is greater than what's available in my knapsack, which means that I'll only be left with one branch. So I ignore D. So it means like my weight remains the same, but my items remain A, B, C. And so I go now, what if C also has the greater weight than the maximum available in my knapsack? Then I ignore C as well. So I'm left with a maximum of C, and AB is going to be my thing. So in this sort of instance, the approach is the same. We have two branches, but you'll always ignore the branch where we include that item when the weight is more than what's available in the knapsack. Okay, the final question we need to ask ourselves is, what are the base cases? So the first base case, the base one, is if we only have one item to choose from. So if you look at my trees here, it's going to keep reducing the number of items available to choose from up until we're left with no items. But the first base case is if we have only one item to choose from, then we only have two choices to make. The first one is we include it in the knapsack if the weight of that item is less than the space available in my knapsack. So that's example, similar to the sort of condition we had there before, which means I'll include it, which means I'll get the profit of the item, or I don't include it, I ignore it if it does not fit my knapsack. So this is going to be my first base case there. And my second base case is when we have no items to choose from. And if we start with 4 items, we'll never get to this particular base case, but I'm just putting it just in case someone just gives us a problem where we have maximum weight and no items. So when we have no items to choose from, then we'll always be getting a 0. And this would be my only 2 base cases to worry about when I'm thinking about this code. Okay, so next video I'll go through the bottom-up approach, but let's put this into perspective of code. And to put it in code, I have to remember how my branches work here. Okay, or probably let me start with the base cases here. So let's start with that base case and see how it goes. Okay, so in my code, you can see I'm here defining the knapsack, and my knapsack is going to take the maximum weight that my knapsack can take. That's going to be the first layer. And then I'm going to take my items, and my items, I have 2 subarrays. So one is the weight of the items, and 2 is the profit of the item. Okay, so let's ask of ourselves of the first base case. First base case is if the length of my weights, right, is equal to 0, so it means I have no items at all, then what I return here is 0. So I'm not going to make any profits if I don't have any weights available or anything to carry there. So that's the first thing. And now the core base case for us is going to be if the length of my weights is equal to 1, and if you remember from the slides, we have 2 choices to make. We include it if it fits the knapsack, we ignore it if it does not fit the knapsack. So we have to check that. And what you're going to check here is if the weight, so I only have 1 item, so that's going to be what's at index 0. So if the weight is less than or equal to the maximum weight available in my knapsack, then I'll be able to return the profit I can get from this weight. Okay, so that's the first layer there. And then the else statement, which I can put it in an else statement, or I can just put a return statement outside my if statement there. Here is, if it does not fit, then I'm definitely going to get no profit from it. So it's 0, so I don't include it. Okay, so those are my two base cases. What is my third base case over here now? Not third base case. Now I'm done with my base cases, so I have to come back to the actual sub-problem. So the actual sub-problem here, we went ahead and said that this only works if the weight of my item is less than or equal to C, and this is going to be the two sub-branches I'm going to have. So let's think about it there. So the condition I have is, so we do this, so we take a tab. If the weight, so I'm looking at the weight of the last item. So I'm always choosing the last item there. So if the weight of the last item, that's going to be index -1, is less than or equal to the maximum weight available in my knapsack, I have two choices to make. The first choice is, do I include that weight or not? So if I decide to include the weight or not, it means that I'm going to take this recursive function plus the profit I get from including that weight. So I'm going to get the profit that I get from that final item, and I add, now here I call the recursive problem the knapsack. But now, because I've included the item, my maximum weight has reduced. So it's going to be my maximum weight minus the weight of the item. So remember, it was weight of D, but here we are taking the weight of the last item in my array. So remember here, so the maximum weight has reduced, it's C minus weight of D. So this is just the weight I had minus the weight of the last item. And now my items also reduced to 3. So it also means that the items that I'm going to put in my function, so the weights of them are going to be 3 of them. So I'm reducing my array by 1 item there. You can go ahead and try this slice and you'll see that it reduces this weights from 1357 and it becomes 135. So there, and also I do the same to the profits. Okay, so that's going to be my first instance where I've reduced my items to 3 and I've also reduced the weight because, but I also add the profit from that last item and then I call my knapsack. And in my second branch, what I did have here was I don't touch the weight, but I reduce the items. So in my second option, I'm not including the profit from the last item because I decided not to include it, but my knapsack, I'm still calling the recursive function. So I'm reducing the weights, but I'm reducing the items, but I'm not reducing the maximum weight available in my knapsack. And what we want to return here is we're going to return the maximum of A and B. So it's going to be the maximum of these two sub-problems is what you're going to get. That's if the weight available can fit, so that sort of final weight can fit the maximum weight available in my knapsack. And the end solution here is, if that does not work out, so this is only works if that's the condition. So if this does not work out, then we come to this problem here, where we say we don't include one branch and we only worry about one branch. And if you look at this code, it pretty much means like the weight remains the same, but my items reduce. So very similar to what I did here at B. So in that sort of scenario, this is exactly what I'm including because I'm not in, I just decide to take one of the branches and this is the branch I'll be taking. And this was the solution for that particular branch. And that's going to be my recursive sub-problem for this particular code. I am done. Probably what I can do is let me try experiment it. What if I go ahead and print? So because the items in, so because I've just used the same variable names as I've named my variable names over here, let me just try print that and see how it goes. In the next video, I'll be adding memoization. So if I do that, I get a profit of 12. So this is exactly the profit I expect to get from here. So I choose 7 as the item. So the last item has the maximum profit. So I add 10, and then it goes ahead and chooses 1. The profit is 2. So the profit there is that. What if I decide to ignore the last item? Okay, so what if I decide to ignore the last item? I'll just go ahead as well and run the code again. And now I'm getting a maximum profit of 11. That means I choose this item, it gives me a 7, and I choose this item, it gives me a 2. Do you remember the sub problem we had? So this is going to be 7 plus 2. which is going to be 11. 7 plus 2 is 9, but 5, the other one is 7 plus 4, because the items can fit, that will give us 11. So that's the better option there. Do you remember the other sub-problem we had previously? So the other sub-problem just had these 3 items, and we said the greedy approach does not work. And we said here, the best thing is to choose these 2 items, and we get a profit of 11. If we take the greedy approach, it only chooses 7, and we get a profit of 10. Does it work in that particular instance? So let's try this as well. So I'll just run my code again, and you can see I get the profit of 11. So my code is working really well. This is just the recursive sub problem. I've not been able to solve for everything. Now in the next video, let's talk about the normalization.